Sure. So our second speaker, let me just introduce you. Yeah, it looks great. Our second speaker is Eslam Khalaf, and he's gonna tell us about Skyrmion superconductivity in twisted bilayer graphene.
Okay.
Eslam,
thanks,
go
Hassan,
ahead.
for that. Thank you. So I'm going to talk today about a recent theoretical proposal we have about a more or less exotic mechanism for superconductivity in twisted bilayer graphene. So this talk will be mostly based on a paper that should appear on the archive sometime later this week. And also I'm mentioning here this other paper which appeared roughly 3-4 months ago, whose ideas were crucial to the development of the insights of the new paper. And both works have been a result of collaboration between Ashton's group at Harvard and Mike Zolotov's group at Berkeley. So let me start by a very brief introduction to twisted bilayer graphene, which many of you probably have heard before. So when we place two graphene sheets on top of each other and twist them by a small angle, a so-called Mori pattern is generated, which have much longer wavelength than the underlying graphene lattice. And as a result, the band structure gets reconstructed in momentum space into a much smaller Brien zone called the Mori Brien zone. And when one looks at the band structure within the smaller Brien zone, one finds that the bands are very sensitive to the twist angle, and around an angle of roughly 1 degree, so-called the magic angle. A pair of very narrow bands appear at charge neutrality, and as a result, correlation effects gets enhanced. Since we have two flat bands per spin per valley, we can fill them with up to 8 electrons. Usually one takes the reference to be charge neutrality, so we have a filling that goes from -4 to +4. And what they do in experiments is they change the filling of these flat bands by applying some gate voltage. And what several experimental groups have now found is that at filling of ±2, so half filling, there is a correlated insulator that appears. Also, almost all of these groups have seen superconductivity in the vicinity of these correlated insulators. Some other groups have also seen superconductivity in other places in the phase diagram. There has also been there's by now a lot of experiments that also some have seen gaps of charge neutrality, some have seen signatures of correlations from STM measurements. So the theoretical description of twisted bilayer graphene starts with the so-called Bistritzer-McDonald model. This considers two graphene sheets twisted relative to each other, and then the graphene Hamiltonian is expanded close to the K and K prime values, so we get a Dirac dispersion. And in this low energy limit, we have actually, the values are completely decoupled. So we have, in addition to the normal charge conservation, we have also a valley charge conservation. This plays an important role. And the two graphene sheets are coupled through some tunneling that has the same periodicity of the Mori pattern. And this tunneling is specified by 2 parameters. To understand these 2 parameters, just look here at this Mori pattern, and you can see that sometimes locally it looks like the graphene sheets are AA stacked, and in some other places it looks like they are AB stacked. And since graphene likes to be AB stacked more than AA stacked, it's useful to introduce 2 different tunneling parameters to denote this difference between the tunneling at AA and AB stacking regions. And using the realistic values of these parameters is that opposite sublattice hopping is roughly 75% of same sublattice hopping due to this preference to AB stacking. However, a very interesting limit was considered in a paper by Tarnopolsky and Ashton. In this limit, they completely switched off this same sublattice tunneling. And in this case, they found that rather than having very narrow bands, they have a perfectly flat bands. And the wave functions of these flat bands turned out to be closely related to the Landau level wave functions. Furthermore, this model has a sublattice symmetry. So the Hamiltonian anti-commutes with a sigma z operator, the sublattice operator, simply because we have switched off the same sublattice tunneling, so there's no term in the Hamiltonian that connects the same sublattice. And as a result, we can choose the flat band wave functions to diagonalize this operator. This means that we have the following picture. So the wave functions can now be labeled by their sublattice index. And furthermore, we find that these wave functions have a Chern number. So for example, if we label wave functions by valley and sublattice, and we have some Chern number in a certain band, by going to the opposite valley and sublattice, which is related by twofold rotation symmetry, we get the same Chern number. And the opposite valley or opposite sublattice, which are related by time reversal symmetry, would have an opposite Chern number. And this leads to a picture that's very closely related to quantum Hall physics, where if we look at one of the Chern sectors, we actually have 4 bands labeled by spin, valley, and sublattice, which have the Chern number and which have an approximate U4 symmetry that relates them. The main difference from a multi-layer quantum Hall system is that here we have another quantum Hall system that lives in an opposite magnetic field that's related by time reversal symmetry. And this difference makes the system pretty unique. For the rest of my talk, I'll consider a simplified version of this model, which is to ignore the spin. So now we have a U2 times U2 symmetry, and this U2 times U2 symmetry can be understood as an independent U1 charge conservation in each Chern sector, and also independent SU2 pseudospin conservation in each sector, where we introduce this pseudospin variable that just distinguishes these 2 bands. Once we go away from this ideal limit, there's 2 types of perturbations one needs to take into account. The first is the dispersion. So in this model, dispersion is assumed to be 0, but the realistic bands have an actual dispersion. And in particular, when we add interactions, it enhances this dispersion. So there's some substantial dispersion. And in the quantum Hall picture, this dispersion appears as tunneling between these bands. It's essentially a tunneling that connects bands living in the same valley, but on opposite sublattices. This type of tunneling perturbatively leads to an antiferromagnetic coupling between these pseudospin variables. This can be understood in terms of a super exchange mechanism, where if both of these bands are full or both of these bands are empty, which means pseudospins are aligned, this term will be deactivated, while if one is full and the other is empty, we gain energy using the standard super exchange H squared over U term. And this term turns out to be of the order of 1 to 2 MeVs. The other effect, which is a sublattice symmetry breaking, the fact that these wave functions are not completely polarized on one sublattice or the other, means that even that 2 wave functions living on opposite sublattices still has a finite overlap. And in the pseudospin language, this turns out to be an antiferromagnetic coupling in plane and the ferromagnetic coupling out of the plane. And it's also the same order of magnitude, around 1 MeV. So this yields a phenomenological energy functional that captures the energetics here, which is just, there's a first term that's related to some pseudospin stiffness that wants the spin in each sector to be ferromagnetically ordered. And then there's these 2 terms that would actually want the spins to be antiferromagnetically ordered and in the plane. So the unique ground state one obtains from this is the XY antiferromagnet, which in the original basis is a so-called intervalley coherent state, a state that spontaneously breaks the valley symmetry. 2 other states that are also energetically competitive that we will need to take into account is the Ising ferromagnet, which is a valley polarized state, so we just fill one valley, and the Ising antiferromagnet, which is a valley Hall state, where we fill one valley in one Chern sector and the opposite valley in the opposite Chern sectors. So this concludes my relatively long introduction. So all of this has been in the earlier paper that we posted in November. Now let's go to the newer stuff. The quantum Hall picture very naturally suggests that skyrmions play a role, because we know in quantum Hall, the lowest energy charge excitations are skyrmions. The question of energetics here is a bit more complicated, and I will discuss it later, but let's now try to investigate what properties do skyrmions in the system have. If we go to this ideal limit where there is no anisotropies, then we basically have 2 decoupled systems with opposite Chern number, which is equal to 1. So a skyrmion in this sector would have charge E. A skyrmion in this sector would have the opposite charge, or alternatively, if we take an anti-skyrmion in the opposite sector, it would have the same charge. These skyrmions, if there is no Coulomb interaction, then they can be of any size. There is a scale symmetry of the problem. If we add Coulomb interaction, then they would tend to be very large in order to minimize Coulomb. So they spread the charge over a very large area. In this case, their energy is given by some universal constant, that's 4 pi times the stiffness, the pseudospin stiffness. Now let's see what happens when we switch on the antiferromagnetic coupling J. In this case, if we have an individual skyrmion, we find that it will pay some Zeeman energy that's proportional to its size. This is because the spins are completely aligned, let's say, in the x direction in one sector. On the other sector, if we form a skyrmion, inside the skyrmion, the spins will not be completely antiferromagnetically aligned. So this Zeeman energy would cause the skyrmion size to shrink and would cause an energy penalty on top of this universal constant. On the other hand, if we form a skyrmion on one sector and an anti-skyrmion on the other sector, we can do this while completely satisfying this antiferromagnetic coupling J, because we can do this if we put the two skyrmion, the skyrmion, anti-skyrmion, completely on top of each other, then the spins locally will be antiferromagnetically aligned everywhere. Most notably, this bound state will form no matter how small J is, because we can completely evade Coulomb repulsion by making these skyrmions very large. And we can always evade J by locally aligning the skyrmion compared to a single skyrmion. And this means we have
I have a quick question here.
Mm-hmm.
So these are real space skyrmions, right? Pseudo-spin skyrmions.
Yeah, they are real space pseudo-spin skyrmions.
And how do you think of it in terms of like a physical picture? Like these are charge density modulations? Or like, I mean, how do you see like experimentally?
This is a modulation of the state. So the state you are in can either be this intervalley coherent state, which is a superposition of electron and hole in opposite valleys, or it can be valley polarized. So you can make such state slowly varying in space, and this is represented by some pseudo-spin vector.
I see. So there is no like, if I were to ask you like, what is the experimental signature of these excitations? Like, can you see it experimentally?
I will discuss a bit some of the properties of these excitations, but one of the main experimental signatures is that the charge would be spread over a large area rather than being a point particles. So these are big objects like of the order of 8, maybe 8 unit cells. And another thing is, if you could measure this, for example, valley magnetization, you could be able to detect this, because the number of flip spins in the spin language is large compared to a single particle excitation, which is the same thing that would happen if these were normal spins. Okay.
I see. Thanks.
Yeah. So yeah, so this picture leads very naturally to an appearance of a bosonic charge 2e object, and this bound state would appear no matter how small J is, and will completely evade Coulomb repulsion no matter how large Coulomb repulsion is, which is the remarkable aspect of this quantum Hall picture. Of course, we have also this other anisotropy term that we have to take into account. So since this term is a ferromagnetic coupling out of plane, it would lead to an energy cost for the skyrmion pair. So here, like inside the core, the skyrmions are antiferromagnetically aligned, but also some of the component is out of the plane, and then this would lead to some energy cost. And as a result, we will have a competition between this J and this lambda term, these two anisotropy terms. But to understand this competition, it's important to first consider the limit where the pseudospin stiffness is the largest energy scale in the problem. So in this limit, we can consider the skyrmions to have a frozen shape. So their only degree of freedom is their size. And in this case, the only thing we can do is just to change their size and change their location. And then we have two options. If J is much larger than lambda, then we will have bound states of skyrmion anti-skyrmions in n plus and n minus, as I explained in the previous slide. If J is much smaller than lambda, then this bound state pays a lot of energy compared to the individual skyrmions. So actually the individual skyrmions would unbind. So we'll have some critical ratio of these parameters for which we'll transition from individual skyrmions to skyrmion pairs. There's another very interesting limit, which is when the pseudospin stiffness is smaller than these anisotropy terms. In this case, we don't, although the topological texture could still represent a skyrmion, which means it's an object with topological charge. We are allowed to deform it in a way that maybe increases the elastic energy, but reduces some of the other energies. And one of the lowest charged excitation, the energetically most favorable excitation in this limit becomes a meron-antimeron pair. So a meron is a, so here we consider the spins to be completely antiferromagnetically aligned, which means J is satisfied. And then in this combined spin index, pseudo-spin index, we have the spins forming a vortex whose core goes out of the plane. And if we have a vortex with a core out of the plane and another anti-vortex with a core that's in the opposite direction, in plane, it's out of plane but in the opposite direction, then this object would be topologically equivalent to a skyrmion, but it will manage to reduce this core energy because now we only pay lambda that's proportional to the area of this small blob. And the cost we pay is that the elastic energy now grows logarithmically with the separation between the two. And we can optimize this distance versus Coulomb and get some number. And we find that in this limit, always the meron-antimeron pair is favored to unpair skyrmions. So in both these cases, we find that there is a wide parameter regime where these skyrmion pairs are actually that the skyrmions bind into pairs which have charge 2e. There's another question, which is the relationship to electron hole excitations energetically, which I will consider at the end of the talk. For now, let's see the consequences of these combined charge 2e objects. So first, a very natural thing to expect is that these bosonic charge 2e objects would condense and give you a superconductor. In order for this to happen, however, they should be allowed to move. If they are completely pinned to place, for example, if they have an infinite effective mass, then they wouldn't yield a superconductor. Instead, they will probably either yield a Wigner crystal or a Wigner glass, so a skyrmion glass. This is important because for individual skyrmions are not really free to move because they experience an effective magnetic field, which means that their dispersion is given by some Landau level dispersion, and they have effectively an infinite mass. However, this pair of skyrmion and anti-skyrmion actually feels a net magnetic field 0. And it acquires a mass through a very interesting mechanism. So this has a very intuitive picture. So imagine you have this skyrmion anti-skyrmion pair moving with velocity v. Then, because they experience opposite magnetic fields and have the same charge, they would experience opposite Lorentz force. On the other hand, since they are bound together, there will be some harmonic potential that tends to attract them together as if there is a spring connecting them. And the spring constant would be proportional to this antiferromagnetic coupling J. Equating these two and substituting back into the energy, we find that the energy would be proportional to the square of the velocity with the mass that's given by the square of the effective magnetic field over the spring constant. This is a more rigorous way to derive this result, which is to write the Lagrangian for the skyrmion anti-skyrmion pair and expand the binding energy to quadratic order in the separation between these positions. And then we find that the spring constant is 4 pi times the antiferromagnetic coupling G. And then if we go to the center of mass coordinate and eliminate this relative coordinate, we can read off the mass from this Lagrangian. And we find a number that's inversely proportional to G, which importantly gives a critical temperature, a Bose-Einstein condensation temperature, that's equal to the product of the density, the filling fraction, times J, the antiferromagnetic coupling. And since this antiferromagnetic coupling is of the order of 1 MeV, this yields TC that's between 1 and 5p, which is the right order of magnitude. The second question we'd like to ask is, what would be the pairing symmetry of such superconductor? We can ask this question because although the mechanism we reach this superconductor is more or less exotic, the type of superconductor itself is conventional because we can have a crossover between this BEC limit to a weak coupling BCS limit. And so we can try to ask what would be the pairing symmetry of this weak coupling superconductor. And this can be understood by a relatively simple calculation. Let me first introduce these Pauli matrices, gamma and eta, to denote the Pauli matrices in the Chern sector and the pseudospin sector. And then let's go to the weak coupling limit and see what type of pairing channels are favored by the interactions that lead to the Skyrmion pairing. So one condition we can find is that pairing has to take place between opposite chain sectors, because as we have seen, it's Skyrmion in one sector and an anti-Skyrmion in another sector. Another more direct way to see it is that pairing in a churn band is like pairing in a magnetic field. So we cannot really have superconductivity in a magnetic field. It's highly disfavored. This can be expressed in an algebraic condition that the pairing function anti-commutes with gamma z, this Pauli matrix for the churn sector. The other condition comes from the realization that this J is the main pairing mechanism, is the antiferromagnetic coupling. So we can write this pseudo-spin operators in terms of some fermions and decouple these fermions in the Cooper channel. And in this case, we find that the dominant pairing channel satisfies the condition that this delta commutes with gamma x. Combining these and considering S-wave pairing, which would mean that delta has to be anti-symmetric, leads to a unique pairing channel, which is a churn triplet pseudo-spin singlet, or alternatively, it's a valley singlet pairing. This pairing can be seen directly from the Skyrmion anti-Skyrmion pair. We can do this as follows. Let's consider what are the transformation properties of the Skyrmion anti-Skyrmion pair under this SU2 times SU2 rotation rule. We find that if we perform the same SU2 rotation in both sectors, in n plus and n minus, that this object is a singlet under this rotation. So it transforms trivially under simultaneous SU2 rotations that's generated by these three generators. On the other hand, if we perform opposite rotations, this would be a non-trivial, this will transform as a non-trivial representation. It would have a finite spin that will generally depend on the size of the Skyrmion. So it depends on the details. And these two properties actually pin down, like together with the S-wave pairing of the gap, they pin down the pairing channel to this unique channel, which we have seen from the weak coupling analysis. At this point, let's try to have a more field theoretic understanding of this system. And before doing this, it's interesting to discuss a duality between this insulating IVC order and the superconductor we have mentioned. So as I said, this antiferromagnetic insulator, so this system has two U1 symmetries. One is a charge conservation and one is a valley charge conservation. This insulator breaks the valley charge conservation, but of course preserves charge conservation. On the other hand, the superconductor breaks charge conservation, but preserves valley charge conservation. And actually, we can do the following transformation, which leaves one valley fixed, but does a particle hole transformation in the opposite valley, under which the valley charge and the electric charge are interchanged. And under this transformation, the IVC insulating order and the superconductor are also interchanged. And this would lead to a dual way to understand the same physics from the point of view of the superconductor. For example, we have said that the IVC merons, which are vortices in this IVC order parameter, which have a core that points up or down, this valley hole core, have an electric charge that's plus or minus E. Using this duality, we'll deduce that the superconducting vortices would have to have a valley charge. Similarly, since we're thinking of the superconductor in terms of condensing charge 2E meron pairs, IVC meron pairs, we can also think of the IVC state in terms of condensing superconducting merons that has valley charge 2E, and that's why they break valley symmetry. And the more symmetric way to understand the relation between these two orders is to introduce an SO5 vector, actually, where the first two components are this IVC state, the last two components are a superconductor, and then we introduce also an extra component for this valley hole state. This is the easing antiferromagnet. And this problem have already been considered in a paper by Grover and Sentil about more than 10 years ago, and they showed that this system will have a waste to minimum Witten term, and which essentially captures this duality between the two phases. It captures the fact that one phase can be thought of in terms of condensation of vortices of the other phase. Another way to understand the same physics is to do a particle hole transformation in one churn sector rather than one valley. In this case, the superconductor maps to an excitonic insulator. And we can see that we have five anti-commuting mass terms. And this order parameters now look very much like here we have an antiferromagnet, and here we have some VBS-like order parameter. And this problem has been considered in the context of normal bilayer graphene by Lee and Sachdev, and they also have derived a ways to mean Witten term for this theory. So let's now consider the details of this theory. So our starting point is the effective action for this n plus and n minus skyrmions. This type of action is known from quantum Hall ferromagnetism. It can, very similar derivation can hold also for the case we have here, with the main difference is these extra anisotropy terms. So let me first just review this action. So this first term is a very phase term that's known in the context of quantum Hall ferromagnetism. This is a term that gives cause to non-uniform spin textures. So it is also responsible for the spin wave dispersion. And these two terms are related to the deviation of the charge from the background. And in the context of skyrmions, these two terms are given simply by the topological charge of the skyrmion. So the plus and minus sector have opposite topological charge. Here they interact via long-range Coulomb potential, and also they couple to the chemical potential. The objects we're interested in are charge 2e bound states forming from anti-ferromagnetically aligning n plus and n minus, which means that to get their effective theory, we should integrate out the ferromagnetic fluctuations, the pieces of n plus and n minus, which are not anti-ferromagnetically aligned. In this case, we get the following effective action, whose main difference is that instead of the linear derivative term, we get now a quadratic time derivative term, whose p-factor is proportional to 1 over j. So j is the mass of the ferromagnetic modes, and this compressibility of this insulating phase would be proportional to 1 over j. A more instructive way to consider this theory is to go to the CP1 representation. In the CP1 representation, we replace this unit vector that lives on S2 with two complex, so a single complex vector that lives in CP1. And this complex vector also satisfies a constraint that its norm is equal to 1. In addition, there is an extra Lie redundancy in this description because we can multiply this z variable by an arbitrary phase, and it doesn't affect n. This would lead to the appearance of some U1 gauge field in this representation, and the topological charge can be written very simply in terms of this U1 gauge field as the flux of the gauge field. We've also introduced this coupling, this dimensionless coupling G, which is related to the chi, the compressibility, and the stiffness. We note that this model corresponds to the so-called non-compact CP1 model, because there are certain monopole operators that may be allowed in such systems which change the skyrmion number, but in this model, this non-compact model, such operators are not allowed due to charge conservation. So we cannot really change the number of skyrmions because they carry charge. And finally, we'd like to also couple this theory to an electromagnetic gauge field using the standard Chern-Simons coupling in order to better probe the physics. So the phase diagram of this theory looks as follows. So we have three phases. One is a pure IVC phase. In this phase, these bosonic Z variables are ordered. They have a finite expectation value. Another way to say this is that their vortices are uncondensed because the vortices would disorder their phase. And the IVC order parameter itself is given by this expectation value of Z1, Z2 star. And saying that Z are ordered means that EMU is in the Higgs phase, or the dual electromagnetic field is in the free phase. So this is non-superconducting or normal phase. There's also the superconducting phase, where we condense the vortices, disordering this Z1 and Z2, and make, and then this would correspond to an unhinging transition of EMU, where A is free, which means the dual variable A capital mu is Higgs. So this is a superconducting phase. This is just the electromagnetic gauge field. However, there's a third possibility, which is not to condense all possible vortices, not to proliferate all types of vortices, but to only condense pairs of vortices in Z1 and Z2. This would still disorder the phase of the Z1, Z2 variable, but it would not disorder the IVC phase, because a vortex in Z1 and a vortex in Z2, their phase would cancel for when we consider this expectation value. So this phase would actually be a coexistence of the IVC and the superconductor. And the resulting phase diagram would look like as follows. So here we're considering the chemical potential and this coupling G. At zero chemical potential, this problem is a relatively well-studied deconfined quantum critical point, where we go directly from an ordered phase, the KIVC ordered phase, to another ordered phase, another superconducting ordered phase. And the reason is that as we tune G, we go through a transition that proliferates the vortices of the Z variables, and since they carry quantum numbers under U1 charge conservation, they would give you another ordered phase, which is a superconductor. However, the physically more relevant case is the more conventional route, where we consider some G that's actually small, because we are having an insulator at integer filling, and then changing the doping to get first into the coexistence phase and then into the superconducting phase. The properties of this transition can be probed within a large N mean field theory. So CPN representations are known to be suited for large N limits. And actually along this line, the large N analysis was done in some classic works. However, what we consider here is a large N mean field theory once you include also the effect of chemical potential. And the main result is as follows. So you can detect this first phase boundary, which is a boundary for which vortices or skyrmions are allowed into the system. You get the following phase boundary, which in the limit of when G is much smaller than the critical coupling is just 4 pi rho s. So this is 4 pi rho, which is the energy of the elastic energy of a skyrmion. Another less trivial quantity that we can extract from this calculation is the superfluid stiffness, which actually gives us the critical temperature. And in general, we can only compute this numerically, which we have done, but we can access a certain limit analytically, which is the limit of small density and also small g, which is, again, this is the physical limit. And in this limit, we find that the stiffness is proportional to the product of the density times J, which gives a critical temperature that's equal to the product of density times J. So this is the same result that we have derived using a very different approach at the beginning of my talk. At the end of my talk, I want to discuss energetics, whether these skyrmions are actually the lowest lying excitations. If we first look at the elastic energy of these skyrmions versus the particle-hole gap, and we go to the Skyr limit, we find that the ratio of these two is close to half. So that's roughly the same as what happens in quantum Hall systems. So there, skyrmions are definitely the lowest lying excitations. Once we go to the realistic limit, this ratio is now between 0.8 and 0.9 around the magic angle. So we still expect these skyrmion excitations to be energetically favorable. On the other hand, once you also take into account the realistic anisotropies, so not just this elastic energy of the skyrmions, we find that the skyrmion energy exceeds the particle-hole gap. However, we notice that this particle-hole gap is only small for a relatively small pocket close to the gamma point. So it's around 30 MeV, but it very quickly increases to around 50 MeV for the rest of the Brion zone. And the skyrmion energy we find from the realistic parameters is in the range of 35 MeV. So this would suggest that maybe once the first few charges we dope in the system enter as electron hole pairs, but at some finite doping that's around 10 to 20%, we actually get skyrmions. Note that our energy estimate for the skyrmions is likely to be an overestimate. We estimate it from this classical energy function, which, for example, is known to overestimate the energy in the case of quantum Hall ferromagnetism. Let me close by some final remarks related to the physical twisted bilayer graphene system. The first is that the mechanism we discussed here is purely electronic, so we don't need anything like phonons or any extra extrinsic mechanism for pairing. We get a pairing of the right order of magnitude already from purely electronic means. Second, although the way we get the superconductor is exotic, this superconductor in itself is smoothly connected to a conventional VCS superconductor. Third, which is probably the most attractive feature of this proposal, is that this large antiferromagnetic coupling is really unique to twisted bilayer graphene compared to other Mori systems like this twisted double bilayer graphene or twisted bilayer graphene when we put it on top of hexagonal boron nitride. And this actually explains some experimental puzzle, which is why do we see superconductivity in twisted bilayer graphene, but we don't seem to see superconductivity when we put this twisted bilayer graphene on hexagonal boron nitride. What happens when we do this is that this substrate induces a sublattice potential. So it favors filling of sublattice A over sublattice B. This means that in this picture we kind of get rid of one of the sublattices. And as you can see, this hopping term that's responsible for this antiferromagnetic coupling would then be strongly suppressed. So in this system, this J coupling is not operative, and that would be our explanation for why superconductivity is only seen in TBG, because this antiferromagnetic coupling, which plays a crucial role for superconductivity, is only operative in TBG. This is, for example, in contrast to phonon mechanisms, which don't seem to have a clear reason why they would be very strongly suppressed when we put twisted bilayer graphene on some substrate. So this is the end of my talk, and thank you for your attention.
Thank you very much, Eslam. So we have now a little bit of time for just maybe two quick questions. Yes, Sabir.
So can I ask a question? Yeah, so when you say antiferromagnetism, just to clarify, you mean antiferromagnetism in valley space, is that correct? Or are you talking about actually spin
antiferromagnetism and Chern spaces between the Chern sectors. So it's not really in valley space. It's antiferromagnetism between the Chern plus sector that has this valley and sublattice combined index.
Right. So physically it corresponds to some kind of density modulation on the Moray lattice scale or on the graphene lattice scale?
On the graphene lattice scale. It would be density modulation on the graphene lattice scale, not on the Moray. All of these are preserve the Moray translation symmetry.
Oh, and your Cooper pairs are spin singlets though at the same time?
Yeah, so I haven't really considered spin in this case. So for the physical scenario, for example, if we're at half filling, then we can consider a setting where the spin is completely polarized. Then these would be a spin triplet, but it's more easing type spin triplet. So we've already broken the spin symmetry and we have only one spin species and this spin species pair. Another interesting scenario would be to consider what happens near charge neutrality where spin symmetry is not broken. And then the manifold of states is much bigger. It's just some big Grassmannian manifold where we can also form skyrmions. And in that case, we could, in principle, have some spin singlet pairing using the same mechanism.
But why did you choose to polarize the spin? Is there some numerical or experimental reason for that?
So the main reason is, okay, so one thing is for simplicity, because the problem is a lot more complicated when you consider spin textures. And another thing is that we believe the state at half filling to be a spin polarized version of the state at charge neutrality. This is also suggested by, for example, these Weitzman experiments where they see these cascade transitions where at every integer filling, you polarize one flavor. So the main option you have at nu equals 2, well, you could polarize valley, but if you polarize valley, you wouldn't really get this inter-valley coherent physics. So it interferes with it. But so the main state that's consistent with this picture is if you polarize spin. So it's a picture like this. So the band structure, we think of a band structure like this, where you open this KIVC gap, which is the largest gap in the problem, but also you polarize spin. And then you're doping here. So you're looking at nu 2 plus epsilon, or alternatively minus 2 minus epsilon. Is it clear?
Yes, thank you.
Yeah. Any other questions?
Is there any other comment or question for Eslam? Okay, if not, let's thank both speakers again, Arpit and Eslam. And thank you everyone for joining us today. So we'll have our next meeting in 2 weeks, and hope everyone stay safe and healthy. And see you guys next time.